presenting, so I'll not be introducing again, so that we have a very short break and she starts right away. Okay, so I'll just start with Chao. Go ahead and you start with your title and everything.
Okay. Good morning, everyone. My name is Chao, and I will introduce 2 years of my life and 100 pages of work in around 45 minutes.
It's a lot for a life.
2 years life. And the story today I will talk about is the wave plus effect on the transition flow of HST gamma theta turbulent model for the wind turbine blade. And first of all, I will introduce some background information for our work, and then I will talk about the modeling process for our safety simulation. Since our topic is about the wave plus effect, so I will introduce a little bit the wave plus concept. Then the turbulence model we used, I will introduce that. And then the results of our main simulation, I will talk in the next step, but finally a conclusion will be given. Okay. Our work are highly related with a wind tunnel test performed by area, and we are using the same wind turbine blade and they did the wind tunnel test. And then we doing our simulation and then get our simulation result, then compare with the experiment data to check our simulation. That's the guideline or process for our work. And this slide shows this is the facility of their wind tunnel test. And this is the blade. You see it's a 2 blade of wind turbine. This is the wind turbine system model for our simulation. And based on many researchers' work, we found that the tower and also the nozzle have little influence on the simulation result of the wind turbine blade. So in our study case, we only studied the wind blade. By doing this, it can reduce the simulation time. That's the benefit. And this slide shows the parameters that we use to build our simulation blade. And you can see this blade is twisted and also tapered. The twist angle, the twists start from the heart of this blade and to the tip part, and it's changed linearly, and the maximum twist angle is around 20 degrees. And the taper also is linearly changed from the heart to the tip. And in this blade, 5 sections from the heart to the tip are selected to analyze in the next step. We will introduce more information about that. After getting the geometry for our CFD simulation, the next step is to find a proper domain and a proper mesh. And in our study case, the proper domain we found is 2 parts. It's a cylindrical rotational domain, and also this is another rectangular stationary domain. This 2 parts is with low mesh density, and this part with the high mesh density. The benefit of doing this is we can reduce the simulation time, and also we can, at the same time, the accuracy of the simulation can be guaranteed. And there shows the dimension of our domain. Slide.
Question there.
Yeah, last slide.
Yeah. So the 20 meters is your 4 times the radius, or 4 times the span of your wind blade, correct?
Yeah.
Okay. Now, in one case, you're showing 2 things. One is with 4R, the other one is with 6R. The 4R is from the blade to the downstream side, correct? Is that, what is the difference between those 2 diagrams?
This.
You have this one and the next one, right?
Yeah.
So what's the difference between the two?
This is just two different different view. This is, we can treat it as the front view, and this is the right side view. And this, the purpose of these two figures just to show you the dimension side of our domain.
Okay, so on the side, from the side view, we are looking at 6R, 2 plus 4R.
Yeah, 6, yeah.
And perpendicular to the direction, then we are looking at 4R. Right?
Yeah. Okay, go on. And a mesh also has a great influence on the accuracy of the simulation and on the software convergency. And in our case, around it's used the different web class, around 80 to 20 million grid are used for different cases. And this slide shows the general mesh on the entire blade and the mesh on different 5 sections. And I mentioned previously, the 5 sections is in the span ratio, respectively 30, 46, 63, 80, and 95 sections. And Y plus is really highlighted with our meshing concept. So next step, I will talk a little bit about the background information about the Y plus concept. Just consider a flow over a flat plate, and during this situation, the boundary layer will be distinguished of 2 different types. One is the laminar boundary layer, and another is turbulent. And between them, there will be a transition region. But in this study case, we mainly pay attention to the turbulent boundary layer. This is our study area. And you can see it's mainly contained from this. It mainly contains 3 layers: the sublayer or the viscous layer, and the overlapped or buffer layer, and then the outside layer. A more clear picture will show in the next slide. This 3 layers. And for our Y plus concept, it is a non-dimensional measurement to describe the distance from the first grid element to the wall. In this picture, from this the wall, and the first layer is located there. And this is the expression for the equation for the Y plus. Y is the normal distance to the wall, and this is the viscosity, this is the shear stress, and the flow density. So when the Y plus value is high, likely the grid will be, the first layer grid will be located in the nth layer. And when the Y plus is smaller, so it will located near the wall. We see it, for example, in the sublayer. That's the relationship. And based on many research work, people found that in the near wall region, the solution variable had a very large gradient. So that means this near wall region, it has very important influence on the result. So to catch the flow behavior near the wall region, Y plus in different turbulence model or different cases, they are always required a less value. For example, some of them always less than 1 in this case. And from the expression in the last slide, and people found the Y plus affected by the flow situation or flow behavior. For example, the density and the shear stress, and also affected by the turbulence model you are using. So in this study case, we want to try to find the proper Y plus value for the SSC gamma theta, this turbulence model. And this slide shows that in this case, we studied 4 different Y plus cases. This shows for these different 4 cases, the near boundary wall mesh, and this there I compared and enlarged the 2 pictures for Y plus less than 1 and Y plus less than 150. And you can see more density near the wall can be found there. And there are 2 points I need to mention about the Y plus. First is that there are actually 3 factors influence the boundary layer mesh. They are the first grid layer, that means the first grid mesh near to the boundary wall where it's located. The growth rate, that means from the first layer to the second layer, or from the second layer to the third layer, how it grows. It grows at the rate at 1.1 or 1.5, the different growth rate. The layer number during this boundary wall, how many layers will you define there? And how many layers do you want to study at this boundary layer? And the second point is, when we do this simulation or casing, first we define different mesh, or this is based on the combine of these three factors. We use different, in our case, we use the same layer number, it's 18 number near the boundary wall. The growth rate, we use 1.15, and we change the first grid layer the distance, and they found a different mesh near the boundary wall. So after the different mesh is defined, then we run the simulation. Run the simulation, we can get after the convergence, we can get the result. Get the result, we can calculate our Y plus based on the equation I mentioned in the previous slide. At that time, we can make sure it's the Y plus value in this region, or this different region. Then we compare, we connected different result with different Y plus. In different cases, we compare our result with the experimental data. And I mentioned previously, this is the wind tunnel test data to check our simulation. That's the guideline of our simulation. This is the turbulence model we use. Because we consider two very important parameters there. I will introduce a little bit about the turbulence model. The model we use is called the shear stress transport gamma theta model. People always also can call it SST gamma theta model. It concludes two parts. One is the SST model, and another one is the gamma theta model. The SST model is a two-equation eddy viscosity model. It mainly combines the K Absorption model and the K omega model. For gamma theta model, it is especially for the predict the transition flow. There are two main important parameters there. They are intermittency and the transition outside real number. This parameter is used to start the process in this model to capture the transition flow during this flow process. Or we can say it consider the onset of the transition. And for this parameter, it's mainly used to transfer the information from the free stream to the boundary wall. That's the function. Okay, now we finished the previous part. Now we'll pay our more attention on the result. We mainly talked about the 8 different results there. We will talk one by one to compare the different Y plus effects on these 8 parameters. First, we talk about the prediction for the flow behavior. This shows the lift and drag force coefficient for the airfoil S809. This is the airfoil we use to build our 3D wind turbine blade. And you can see from around -6 to 6 degrees. This is the CL, the lift coefficient. It increases linearly, and while the CD, which is the coefficient of drag, it keeps always constant. And in this region, the flow is attached with the airfoil. So we define it as the attached region. And from 6 to 15 region, both the CL and also CD, they increase, but non-linearly. And the transition or separation may happen there. We define it as the transition or separation region. And as the air angle of attack increase for one airfoil, stall may happen. And the definition of stall is that it's a decrease for the lift force coefficient. And the angle of attack increase after it achieved a certain degree angle of attack, the stall will happen. And stall is mainly will vary based on different airfoil, based on different flow situation, and based on different real number. And in our case, you can see the CL decrease from 50-degree angle of 10. So it starts the dynamic stall region. And then in around 20-degree angle of 10, there is a significant change in the trend of CL and also CD. It indicates the beginning of the deep stall region. In this deep stall region, for the entire airflow, all the flow is detached or separated. This is for the 2D airfoil prediction. And this slide shows the entire 3D blade prediction for the flow behavior. And you can see stall started to affect start around 10 meter per second case. And it's mainly affect for stall 3 cases, 10, 13, and 15 meter per second case. And the intersection for 20-degree angle of a tank with these 3 cases is located around the second section we mentioned previously. It's around 46. This is around 70, and this is around 90% span ratio. These 3 points we will mention that in the later result. And the 25 meter per second case, you can see it's totally in the deep stall region, which means for this speed, when the speed cases, the flow in the blade will be totally detached or separated. This is our prediction for the flow behavior. Now we talk about the second one, the streamline of the result. Streamline are the curves that tangential to the velocity vector of the flow, and they show the direction of a flow element which it will travel. In this contour, this kind of contour is in our data parameter showed the detached flow, and this vertical line is the attached flow, and the region between this and the line is the transitional flow. So we can see for these 4 different cases, 1 plus less than 1, then 5, then 30, and 150 different cases. The main difference mainly located in these 2 cases is this is the transition 20 angle tank for 20 degree, and this is the transition region predicted. But for these 2 cases, the transition located there and there, so a little misprediction there. And for 30 meter per second case, for our suction side, the main difference also located in these last 2 cases. You can see this transition predicted in these 2 cases, but this is a little forward and a little forward. So, and then in the last case, since we can compare the region, but the little attached flow happened there. And for 15, it's similar to the last case, 30 meter per second case. But there little transition predicted in the first 3 cases, but for the last case, no transition happened there. For 25 meter per second case, as we mentioned, it's totally detached and separated, so no transition happened there. So the difference is not clear. It's similar contour have predicted. These 4 cases is for the suction side. Now we come to the pressure side of the window blade. You can see for the first 3 cases, similar contour, just for the last one, different contour, the no transition have predicted there. Also seen in the last case, no transition predicted, and for 15 meter per second case, similar with the 31. And then for 25 meter per second case, since it's totally separated, detached, so no transition predicted in all the case. So we make a little summary for this parameter. we found for the same contour predicted in all the cases, but for the 25 meter per second case, and for the last y plus case, y plus less than 150, it's failed to predict the transition flow in both the suction side and also in the transition side. Now we come to the next parameter. This shows the 10 meter per second case and the contour in this slide. When it's the dark blue contour, that means it's a detached flow. We can compare with this. And the yellow contour means the attached flow, and the region between them, that's the transition region predicted. So we compare these four cases and found the main difference in located in y plus less than 150 case. It failed to predict the onset of the transition onto the leading edge. 30 meter per second case, and you see the contour, the main difference also located in the last case. The attached area, I mean the yellow contour is a little smaller. The next 15 case also similar with the 13 case duct, and the area is much smaller, and the 25 is similar. That now is the suction side, now is also the pressure side. Pressure side for this parameter, since the attached flow is dominant in the pressure side, so similar contour predicted in the four different cases. In this 13 and 15 meter per second case occurred in the 25 case. So make a summary for this parameter. We found the difference in the suction side for this 10, 30, and 15 case is mainly located in the last case, the y plus less than 150 case. And in the pressure side, similar contour predicted. Then we come to the intermittency, another important parameter. In this parameter, the first case also is a 10 meter per second case. The light blue contour is the detached flow, and this dark blue contour is the attached flow. And for this last case, the red contour is the detached. This is the attached flow. And so we compare. We found in the last case also no transition predicted. It only have these two contours, attached and detached. For 30 meter per second case, last case also no transition predicted there. But this we found in the y plus less than 30 cases, the incorrect prediction with compared to the first two also happened there. And the 15 meter per second case similar with the last case. And for 25 meter per second case, since it's totally detached and no transition happened there, so similar contour predicted. Now we come to the pressure side for this parameter. We found the first three cases similar contour predicted, and no transition predicted in the last case. This is the similar result happened in 13, 15, and 15 case. Let's say 13 and 15. Just and the wind speed increase, the region for this part it will become smaller and smaller. And for 25, since it's totally detached, so the difference not exist in this 25 meter per second case. So to sum up for this parameter, same contour predicted in all the 25 meter per second case, and the y plus showed the inaccurate in predicting the transition flow in both the suction surface and also the pressure surface. In the other two cases, 30 and 15 cases, the y plus less than 30 showed a little difference with the first two cases. Now we come to the coefficient of tangent force and the coefficient of normal force. These two important parameters. We're almost there. The tangent force is a force that parallel to the airfoil chord line. So this is for 10 meter per second case. You can see around in this red point is the experimental data, and this is our result. And we also compared with the result from other authors. The main difference happened in this part, around 46 section, the second section of the wind blade. All the simulation overestimated the result than the experimental data. And many researchers had found the reason. They call it the slow delay. The reason can be explained in this way. For example, in 10 meter per second case, the intersection for 20 angle over 10 is around located in the second section, the 46th span ratio, where is in this slide the error happened in this section. And in 20 degree angle over 10, and the angle over 10 prediction for this point, the C error, it should be decreased in the experimental data. But in the simulation, the flow will still predicted is still attached in the airfoil. So if at that case, the lift coefficient will be still a little higher level, higher value than the actually value. And the CT, the tangent force coefficient, is proper to the lift force. Since this remains a little higher value, CT will, in the simulation, will keep a little higher value than the experimental data. That explains the second section higher value. And this slide shows for the 13 and 15 meter per second case. And you can see for the Y plus less than 150 case, the difference showed in the tip region in these two cases, and for 30 meter per second case, it showed in around the middle span, around this camp is the same reason, can explain from the same reason at the 10 meter per second case. The safety is highly affected by the separation, and for these two wind speed cases, 13 and 15, the separation of the intersection with the 20 degree angle over 10 located in the middle span and the tip region, which caused this mismatch. In 25 meter per second case, we found the main difference located in Y plus less than 30 case instead of the 150 cases. And the reason for this is when it's the Y plus is located in 30 cases, it's the case. This part is a buffer layer for Y plus. It next to the whisper sublayer and the inertial layer. And for these two different layers, the people use different solving model. They use wall function model and the low real number model to solve these two different regions. So when it comes to this buffering layer, these two solving model is combined there. During this combining process, some mistakes or some unsteady result will come. So many researchers say that this may cause the mistake in this prediction. Now we come to the normal force. Tangent force, CT, or tangent force coefficient, is highly affected by the separation, but the normal force, since the direction is vertical to this flow, so it's less affected by the separation. So in all the cases, you can see similar result with the experimental data, the red point achieved. This is the 10 meter per second case, 13, 15, and 25. All the results showed good agreement. So we make a summary for this two parameter. Cn, the normal force coefficient, is less affected by the change of Y plus value. And for the tangent force, the disagreement happened in weight class less than 150. This is mainly caused by the separation. And the disagreement in weight class less than 30 is because it located in a buffer region. Okay, now is the last important parameter, the torque and the thrust force. This is the result for the torque. And you can see in the low wind speed, it's good agreement. And for 10 meter per second case, our wave class cases, this is showed better agreement than the one from another author, the red point. But a little difference with the aerial experiment still exists there. And the reason this can be explained also by the stall delay. And this disagreement is inconsistent with the tangent force coefficient. As the grid becomes closer and closer, for example, from wave class less than 1 to 150, the error or the disagreement also increased. So compare these 4 different wave class values, we found the wave class less than 1 case showed better results than the other 3. And another point is the wave class less than 150 case showed better agreement than with the experimental data than the case that wave class less than 30. And you can see this is 50, this is 30. This comes from these 2 points. For the torque, it's equal to the tangent force times the distance or times the radius. And in wave class it's less than 150. You can see this is the 50, it's a red line. It's in the half or in this region, the value is higher than the experimental data. But in the tip region, the value is a little less than the experimental data. This is the coefficient, and also happened in these 2 cases. But for wave class less than 30 case, the value always showed higher than the experimental data. Since this tangent force coefficient for 150 is higher in the half and lower in the tip, and for this equation we have seen if it's in the tip, the value in tip times the distance. The distance is the location that with the half. So when it comes to the tip, the distance will be higher. So when it times the value, it will have more influence, which means the value in the tip region plays a more important role in this calculation. And for wave class less than 150 case, it showed lower value there. So in the overall result or value for this, when we calculate the torque, the value for this wave class less than 150 will show a little lower than the wave class less than 30, so, which means it will a little better match with the experiment data. That's the explain the wave and the torque value. It showed better agreement. Now we come to the thrust. And you can see different wave class values in thrust showed good agreement. This is the other people's work. This showed our work. And the thrust is integrated from C and the normal force coefficient. Since we get good agreement in the normal force coefficient, and the thrust is very connected or calculated from this parameter, so it also shows good agreement with the experimental data. And our results match the experimental result, also showed better agreement than the other work. This value is from another people's work. till now we compared all the 8 parameters and finalized with the influence of the Y plus. So give a conclusion there. The main purpose of this presentation is to evaluate the Y plus effect in this basic model. And we found for the overall performance, the highest grid resolution, that means Y plus less than 1, showed the good result in all the cases. And the Y plus less than 150, it shows not predict well compared to the other three. And it's in the intermittency, transition, onset real number, and the streamline. These 3 parameters. And for this Y plus less than 30, it shows a little incorrect in this 2 parameter prediction. And the good result for all the Y pluses in the normal and the threshold, since it's less affected by the separation. This is our conclusion. And in the next slide, it's based on the work of these 2 years, we published several papers. This is the paper we went to ASLES to San Diego. It's a part, another part of our work. And this other 2 is including the pathway student sympathy. And this 4 and 5, we have already submitted one, but haven't received any response, and this is accepted. And the work based on this presentation, we will submit for a paper. We will wait for the response from this one, then decide which journal we will go to. And that's all the work for my 2 years. Thank you.
Questions? Anyone?
Yeah.
In your presentation, you have the range less than 500. That's real.
150.
150, and another is range less than 30. What is the difference between them? We know 150 and less than 150, the also including
No. Oh, okay. That point is the Y plus value for Y plus less than 150 and the Y plus less than 30. Less than 30 means it's we do the, as I mentioned, the process we calculate the Y plus value. First we do the different mesh on the boundary layer, and then we do the simulation, we get the result, then come back to calculate our Y plus value, right? When we calculate the Y plus value, we can't get, for example, we say that we want to Y plus equal to 30, but sometimes we get the 29. It's also acceptable. So we use people, and this is the common way people researchers work for this part. Y plus less than 30, we achieved the Y plus less than equal to 29. That's the Y plus for less than 30 case. And for we said Y plus less than 150, that means we achieved the value around Y plus equal to 148 or 149. That's the case. It's not. It's very close to this value, but it can change a little bit for 1 or 2, but not if you said for the Y plus less than 150, it should not close to 130 or to 30. It should close to this value.
I think let me clear one point. Y plus is a non-dimensional parameter. One of the parameter, it's a non-dimensional group. One of the parameter is the distance of the first node from the surface, okay? But it also includes, the non-dimensional group includes some flow parameters. So what physically you can do is change your grids to change that distance, okay? But suppose your intention is to get something close to 150. You changed it higher. It's directly related.
Grid size, right?
Grid size. Start first point. First grade from the surface. But then the flow parameters can influence it and may bring it to 45. So what you are essentially trying to look at is, you're trying to look at results for a case where the first grid point is a little bit farther away from the surface compared to a point which is closer to the surface. Okay? So you identified few points. Let's say 30 is one indication and 150 is another indication. Then you do some trial and errors. And these are big trial and errors because you have those, you go through all the procedure, simulations and all those things, and then see what Y plus is. And if that Y plus, suppose is going for 30, but came out to be 45, that combination is gone. So he changes the grades, okay, and then starts again to see if something is very close to 30. So essentially he's trying to look at if the first point is at this distance or in this range of distance, what is the effect?
So if I'm looking at net benefit, then the higher the Y plus value, the less the simulation time. Right?
Yeah, you can see that.
Right, so I'm saving simulation time by increasing the by increasing the grid size.
Yes.
Right?
Yes.
So is that significant enough between going from Y plus value of 30 to 150? Of course, that's a big jump. But is that significant savings in
Simulation time.
Or what I meant is that worth increasing the grid size? Because all the values from your graph, pretty much everywhere, 150 values are
Not as good.
yeah, everywhere up to 30. Then I'm also wondering why you went from 30 to 150 and no value in between. Seeing that the 150 is always a little different from the rest, so there may be another point which is more optimal.
You mean why we don't choose 120 or 100, right?
Somewhere there. So two questions.
Okay, so one by one. Actually, many researchers who did this kind of work, people always use this different range. And the second factor is, yes, you can define it by yourself, but if you define another parameter, it's hard to compare your work with the other people's work. So people follow the same rule. It's kind of a rule. They use the same parameter. You can define by yourself 100. I just like 100. That's fun. That's okay. But many people they study different model. We are using this SAT gamma theta model. People use just SAT model or use the K omega model, K visional model. They study different parameter, different Y plus K, and they pick up different one. So
they always use those 4 Y values. Okay. So, but if from your study, if you think there is a reason why we should look at a different Y plus value, no, nobody says unless this is a standard and there's nothing that can be done about it, then okay. But otherwise, just because somebody else, 5 people before you studied and they used only Y plus of 150, doesn't mean we have to stick to the same Y plus, right?
Yeah, you can.
So if there is a reason, meaning everywhere 150 is off, so there may be another point between 30 and 150 that may make more sense.
I remember I read a paper about this. They said this 4 point is not selected by people just randomly. I like this paper, like this number. It's based on some work. It's from Germany, the Dr. Minter. They studied that at this 4 point, and also I showed the Y plus figure. You see these 4 different points and the 4.
So the direct answer is it has a physics behind it. 1 and 5 is in the sublayer region, laminar sublayer region. 30 is in the buffer region, and 150 and above is in the turbulent.
Yes,
so
yes.
It's looking at those.
Yes.
So is that the fully turbulent layer? Is that the first point you would get in a turbulent layer? No, right?
It's not the first point, but the equations, the models that they're using, Y plus 150 and above, your 30 and above is in the turbulent region. So if you go to 150 means you're fully turbulent. Now
30
if you
is transient?
Is in the buffer region,
okay.
and which is a bad region because it's just 2 equations are merged to represent it. So obviously if you go to 0.01 instead of 1, you get much more result.
Sure.
But your second better result. But your second question you didn't answer. How many nodes you used?
I mentioned in the mesh.
Answer again.
Mesh size.
What
Okay.
is the mesh size? You might not have listened.
Yeah, my mesh
Or that.
size.
What
Okay.
was the mesh size?
I used around 18 to 20 milli.
So if
Yeah.
you change a little bit, it changes drastically the calculation.
Yeah.
It's about 18 to 20 million.
Yes.
By going.
No, well, total number of nodes, if you have like the calculations that you are doing was 18 to 20 million. So if you go to 0.1, you get the result. You can reduce and make it bigger on the outer surface. Okay, but you'll have a total number of grids to be much more. But if you can go to 150, your total number of grids will come down.
Yeah.
The only thing I want to ask is, what are your recommendations for further work?
Recommendation for
For
future
further
work.
work, based on
That's an important point. I hope you have.
He put it in the thesis.
Thesis, yeah.
Yeah.
What is it answer? Yeah.
Don't remember?
Actually, after we figure out the different weight class effect on different parameter, and we can see some parameter affected by weight class less than 30, and some parameter more affected by weight class less than 50. So in the future work, if we want to study the parameter that is related to related to the 30 weight class less than 30 that parameter, we can see if this weight class less than 30 have big influence than in this parameter. We will get the suggestion or get advice that we can't use this weight class less than 30 case. We need to change the value, the mesh. For example, weight class less than 5 or less than 1, then we will get a good result. And alternatively, if we want to study some parameter that are not related to the parameter we studied in weight class less than 150, we can use this a little close mesh because it's not affected in the mesh. So it can reduce the simulation time. Also, it can we can get the acceptable result, right?
But I think you still didn't answer what the next person.
No, actually, before you go there, you know what is your first recommendation? The question I asked was your first recommendation. Adding more y plus value cases.
Well, we can do that, right? And with this study, we just applied for for this specific turbulence model. We can also study on the other turbulence model. And many people study different airfoil. This one we call is the wind blade is the aerial field 6 wind turbine blade. This is a specific wind turbine blade. After getting this support from this simulation, we can apply this theory to the other wind turbine blade, right? That's all the future work we can do.
So why did you choose SST gamma theta instead of the other model?
Okay, good question. First, it combined two different models, SST gamma theta model, SST model and gamma theta model. SST model, it also combined two models, K omega model and K epsilon model. This is comes from for example, 20 years ago, they only have this K omega model. Then 10 years later, they have this model. Now they have SST model. It combines the advantage of these two models. So this SST model shows better behavior than the other model. At the same time, recently, 5 or 10 years ago, the gamma theta model came. This is especially, as I said, can predict good parameter for the transition flow. This is for the separation flow. So we can use the SST gamma theta model. We can predict both the separation of the transition, predict all the flow behavior. That's the very perfect model. Most of the situation, for example, if you want to make it easy, you just use the SST model. In this June and July, we go to the San Diego, California, go to the ASME. And in the conference, the students from the Texas Tech, they just use the K-omega model and doing the simulation, then present their result. So people, if you want to make it easy.
So now that comes back to your recommendation.
Okay.
So if this is so good model that it incorporates everything and all the 20, 30 years of work, then why are you suggesting that we should study SST model, KE model, K omega model? Just now you said all those things are not as good as the one you used. So why are you suggesting for some student that follows you, hey, go back and look at those really bad models?
Good question. And we can see from this point, this model shows good behavior of advantage in predicting both separation and transition. This is for the wind turbine blade case. But what if you want to study just the simple objective? This blade you can see is twisted and also tapered. The shape is very complicated, and the process to get the geometry takes lots of time. If you just want to study, for example, this bottle, it's so simple, just a cylinder, for example. You don't need to use this very complicated model. Another model, for example, K omega model or K Vishnu model, it can also vivid to simulate the flow situation, and the result also acceptable. And it's much easier for the people to operate, and also sometimes the calculation time can be reduced. So that depends on the different study case. But if we want to study the wind turbine blade, use this thing, just this model, the K omega or K Vishnu, some problem or some parameter, some flow
because
behavior.
you are not able to take the
All the
shift. Right?
yes. So that depends on.
Or you do not know whether your SST gamma theta model actually predicts better than just a K epsilon model for your case.
Okay.
Did anybody do the work?
Is there a comparison between
Compare-
K
you didn't
epsilon,
compare
K
anything.
omega, and SST model?
But did anybody use, I guess, did anybody use this model
For
this
feasible.
model for this kind of scenario and compare it with other models?
Yes, many people did work. The previous, this is SST gamma theta model. People use SST model, and some older paper also they use the basic model. And when you read this paper, you can see the improvement. And also, one point is the paper for example, the previous model, K omega model, they showed we use this kind of computer, we use this model, we run the whole long time. But at the time going on, the computer more powerful, and this turbulent model also works.
So is it a generic simulation, or it was on a wind turbine blade with these parameters, with this twist and with this taper and with this span? The improvement that you show is a general CFD prediction improvement on any flow or specific flow, specific for to your geometry, to your condition.
As far as I remember, both happened. People studied both cases.
No, it's not.
So nobody did the kind of work you did? No?
I haven't read any paper about this. Even some people studied, yes, some people studied the Y plus, but they didn't study on this blade. Maybe people studied in this blade, but they didn't study the same parameter as we did.
That's what he's trying to make you say. Like you did something that others did not.
Yeah, we did something that people didn't.
So you are suggesting then that these other models should be applied to your situation because you are recommending. See, you are recommending for future work. So if there are other models which you didn't use, perhaps if they want to test it to see how.
So your future students should also test them. And the final conclusion.
So you should rewrite that section to reflect the fact that you use a particular model for your specific situation, but there are other models which could also be tested to see how, and then the results compare. That could be a recommendation.
Compare different models to show the.
Yeah, to your,
For your specific.
for your specific.
Okay, I get it.
Yeah, that's why you were using the model to show that it could be slightly different nonsense. At least that's how I understood.
Yeah. Yes. I see.
So your parameter was Y plus, but it was not different models. You just chose what you think or what you know is the best model. Okay? But for your particular case, these combinations, the sophisticated, combining all the effects, may not be the best predictive model.
Maybe.
Okay, so you haven't studied that. So that could be one of the recommendations.
Yes.
If somebody has time.
Yes.
So, yeah, I would suggest the same. I would like for you, even though that might be a big deal, your recommendation should not be, if you already looked at it and you discarded that it has no merit, but telling somebody you should look at it, then it doesn't make sense in my judgment, right? So, look at your recommendation. So, what degree are you getting? What is the degree that you're trying to get?
Master degree.
Complete name, what is the name of your degree?
Master of Science.
Master of Science?
Master of Science in Engineering.
In engineering, right?
Uh,
So you wrote Master of Science in Mechanical
You know, it's
So
a
we
general.
don't have, even though some of the mechanical engineering professors think they have, we don't have Master of Science in Mechanical Engineering right now. The degree we have is
It's coming
Master of Science in Engineering.
Isn't it, Dr. Bird? MS in Mechanical Engineering, at least before environmental, coming soon.
Yeah.
Coming soon?
Yeah.
Yeah, but right
He's
now,
gonna get a right?
right now,
We are just engineering.
yeah, Master. So you put Master of Science in Mechanical Engineering. Okay? You don't have that degree right now. So the degree you're going to get is Master of Science in Engineering.
Before I come, they didn't tell me that.
Nobody else will tell you. You need to find out.
Yeah. Okay.
So you applied for admission to Master of Science in Engineering. You need to go back and check your application.
Actually, you can get it on the website.
Okay, and Tradi is not acting dean. He was dean
Just
For-
copied it from somebody else.
for, no, but Dr. Tradi was never acting dean. No. He was dean for
That was
15, 20 years and he retired. So we have Dr. Akujodi who is the dean. So you put Dr. Tradi, acting dean, College of Engineering. Again, these are minor things, but
very important.
okay, so you need to pay attention to those kinds of things. And I have some comments that I will talk to you separately
Okay.
about your figures and that kind of stuff. Lot of comments on those.
Okay.
So I'll talk to you about that.
Any more question?
Yeah, okay, before I go, I was just wondering, since I'm not in the field, to see what explanations you have for the deviations, the deviations that you had. Some didn't predict very well, others did fairly well. And so, what explains the deviations from the predicted results? Some of them you recommended that the predictions were very good. Others were not that good.
Yeah.
So, do you have any, does the literature point to any reasons, or is that because the model is not, the problem is the models that you're using, and that they need to be refined?
You mean why some pretty good, why some pretty
Yeah.
bad?
No, in your graphs, you can go to some of the graphs where you
Try to
show
give
some
some
experimental
explanation.
data.
30.
Okay, right there. So you see the good bit of deviation, right?
For example,
No, go back to another figure. See those dots, those circles are the experimental data, right?
the red point is
Yeah, the red circles are the
the experimental
experimental data.
And I see this two part has
Yeah, but if you ask me, I'll say no, they are not predicting very well.
yeah, I said these
But
two,
you said
these two parts doesn't.
Listen to the question first.
Okay, so the question he is asking, and now that he is asking that I see here, you are saying that these models, except for the y plus value less than 150, everything else is pretty good, right? But when I look at it, I don't think, at least again, I'm not an expert in the field, but I feel, no, it doesn't look that great. So what he's asking, those deviations,
Are they acceptable deviations?
yes, that's what he's asking.
Okay, why we say it's acceptable? We also compare our way different way plus value with the other people's work, and you can see.
All this is your work, but we are only looking at your work with the experimental work.
How can we know is our result is acceptable or not? We showed our result and the experimental data result, and then we compare with. We also include the one result, the simulation result from another author,
Okay.
and they.
Where is
But-
it? It's not here. But even if it is there.
If it's there, it doesn't still explain it.
See,
Because
for
it
example,
gives-
if I look there, for the span ratio of 0.3 or something, right? Your data says let's say 1.8 or something like that, right? Excuse me, the experimental data says 0.18, 19, something around that, right? But all your models with different y plus ratios, still they are very high compared to this. Instead of 0.18, they are ranging from anywhere from 0.25 or
Some are twice.
some are
twice,
double.
or more.
So why should I think that your model is pretty good when it is so far up? So what makes me think, or what explanation do you have for us to think that yours is okay?
Yeah, that's what I said. Our results may show the disagreement. We put the other author results there, and the other author when they do the simulation, they also show the disagreement. And we found our result showed better than the other author. That's enough, I think.
Okay, you mean yours
Yours is better
predicts
than.
it better, but
Yes,
still,
yeah.
but still.
Yes, it's the disagreement with the independent
Okay.
data.
So all those predictions are from borrowed models. You didn't develop the model.
I didn't.
So among this model, the model you used with the proper y plus condition
And the mesh.
is giving better
Better,
than
that is
the-
what you can say.
the other authors.
Yeah,
You didn't develop any model.
we didn't.
But is it within all acceptable, and was there anybody whose work was, say, 5% from experiment? No. Almost all of them had this much deviation, and
Yeah.
that's the accuracy of the model.
Exactly.
Yeah,
So what about the trend then?
we just the user, not the developer.
Sure. What about the trend? So when the span ratio increased, the tangential force coefficient came down and then it went back up. Is that a readily acceptable trend? Right?
Yeah, this trend, if we really care is the rate point, is the experimental data. The experimental data to get a big trend, come down, then increase.
Yeah.
So you follow
And
it.
you got the same trend, so is
Yeah.
that a fairly acceptable?
Yes.
Yeah, that's from the physics.
Yes,
This is
that's
what
right.
it is there. But I think one thing also to be added is this is the first experiment that was done to include 3D effects. And so the experiment, still there are questions whether the experiments were very accurate or not, because it is very difficult to have 3D field effects on large scale wind events. Okay? So this was the first one where actually they were looking at, before that it was all 2D results from where they were predicting.
So you're going to capture all that in the thesis. Because these are very important points in English. You're taking notes. It's very important.
Let me ask you about your domain. Is there
Very good.
the domain that you have chosen, is that the optimum domain, or can it be
Change, right? The
can
shape.
it be changed to make the model more effective?
Actually, the domain, nobody said this is the best or another is the best. Different. And for the paper and I read, and there some people, sometimes the people just use the cylinder domain, the wind domain, and they
Just the rotational
yeah,
field.
they showed the result not as good as this one, but it's also okay. And sometimes the people use different shape. This is the cylinder. Sometimes people use a
Cylinder.
circle. They use a different shape. People do that, and they also see the result. They showed some part of the result acceptable, some part have the derivation. But most of the people use this domain, the result show the better agreement. So we take this one. No people said we have to use or have to use that one. That's you define by yourself.
Sorry. See, 4 times the diameter.
If I reduce that to, let's say, 2 times, will that change? I know it would reduce the simulation time, but will that lower the...
Again,
General acceptable thing is this is actually one of the, if you go below that, you will deviate farther from the ideas. Okay, so a normal practice of all those kind of things is about 5, and sometimes on the downstream, a total of 10 times the diameter. Okay?
But you can increase the grid size there, right? The mesh size, when you go farther.
No. Farther, yeah, you can move, but close to the blade,
Yes, you keep the-
still have to have those things.
Sure. But as you move away, is that something that you can keep changing?
Yeah,
as
that's
you go
what
further?
they are also doing. Okay, you will have to increase the grid size. I mean, you do increase the grid size, but you can get a reasonable amount of, it's a 3D, so if you increase it by 1D again,
Then,
grid size just goes beyond the roof. So that's a sort of minimum thing that is needed 4 times or twice in the diameter area, in the cross-sectional area, normal.
actually, in our group, we also did some work to study
Dr.
Dr. Lee.
Some work was done by Dr. Lee, and he then
looking
came
at
up.
different.
the influence of the domain sign. We consider 6 meter or 20 meter. What's the difference? We also did some work. It's not.
That should have been your first answer, you say.
Yeah. Okay. That we didn't include in this presentation.
So in fact, any CFD results you do, domain independence and grid independence is an initial step.
Yes.
And he did some of that. All right. So before Shravanti starts, I don't know about you. I'll take a small break and get something to eat. Okay. And then we'll start. Okay.
Okay. Thank you, everyone.